A dinghy is pulled towards a dock by a rope from the bow through a ring on the dock 6 feet above the bow. The rope was held in at a rate of 2 feet per second. So here we have a picture, and this one is 6. And so we could call this one R and this one X. R is for the length of the rope, and X is for the distance from the dock. Okay, one of the things we're given is the rope is held in at a rate of 2 feet per second. So the rate of change of the rope, dr dt, is negative 2 feet per second, negative because it's becoming shorter. Part A was how fast is the boat approaching the dock when 10 feet of rope are out, but we're going to work on part B on this one. At what rate is the angle changing then? So we see we have this angle theta, and what we want to do for our specifics is we want to find d theta dt when there's 10 feet of rope out, so when R equals 10. So we're going to deal with that in a minute, but first let's look at our picture, and the things we're interested in are the angle theta and the rope length R. So looking at this triangle, we want to make a connection between R and theta, and I can use right triangle trig, and I'm going to use 6 because I know that. That's the adjacent side, and R is the hypotenuse. So I know that cosine of theta is going to be adjacent of 6 over hypotenuse, which is R. Now I'm going to get rid of the fractions and write it as R cosine theta equals 6. Now, this is my connection between R and theta. If I now take the derivative of both sides with respect to time, I will have my related rates equation. And I can see that this is a product, so I need to do the product rule. First times the derivative of the second. The derivative of cosine theta is negative sine theta times the derivative of theta, so d theta dt, plus the second function, which was cosine theta, times the derivative of the first, which the derivative of R is dr dt. And that's going to equal the derivative of 6, which is 0. So there's our connection. We're going to want to find d theta dt. So let's solve this for d theta dt. We can move that term over to the other side. In the interest of room on the slide, I'm just going to erase this and put this equal to 0, and this won't be negative if I moved it to the other side. Okay, so now since I'm trying to solve for d theta dt, I'm going to divide by R and also by sine theta. Okay, now we're ready to look at our specifics. We're going to find d theta dt when R is 10, and this is cotangent, cosine theta over sine theta. So let's look at the triangle, and when R is 10, so we're looking at a specific case in the triangle. When this is 10 and this is 6, I recognize this is a 3, 4, 5 doubled right triangle, so that's 8. But you could do Pythagorean theorem to find that if you needed to. But we need cosine theta over sine theta, which is cotangent theta. And so here was our theta up here, and cotangent is adjacent over opposite, so that's going to be 6 over 8. And then we also need to have, we're dividing by that R, and that R was 10. And then we have dr dt, and dr dt was negative 2. So now we can just compute that, and we get, we're going to round to 2 decimal places, negative point, so 0.15, and this will be in radians per second.